Hello, my name is Liam Pocher and I am from Los Alamos National Laboratory. Today I'll be giving you an overview about some of the implications of numerical operator mutation of differential systems. The three main topics of discussion today. First, we will discuss locally negative entropy production. Second, we will discuss semi-analytic recovery of viscous wall heating effects and how semi-analytic heat conduction produces an opposite wall heating effect, and how combining viscosity and heat conduction effects reproduces an effective approximation to the analytic inviscid solution. We will thoroughly discuss the mutation of differential systems by numerical discretization, which is presented in the context of semi-analytic, numerical, and von Neumann artificial viscosity comparisons. Now we will discuss the equations that were discretized and the deployed numerical algorithm and its verification. Why would one want to understand how numerical operators influence a numerical solution's behavior? Well, numerical solutions are used everywhere from industrial applications and design to government agencies answering questions about national security. Partial differential equations can have numerical discretization that add extra terms that mutate the underlying analytic differential equation into an entirely different differential system. This is readily apparent in von Neumann's artificial viscosity and in upwinding, both of which mutate the inviscid analytic Euler equations into an effective viscous Navier-Stokes equation. Extra added terms in differential systems have effective numerical coefficients which approximate physical quantities such as the Reynolds number for viscosity or the Peclet number for heat conduction. These examples just happen to be physically dissipative quantities. Numerical methods such as artificial viscosity are often used for stability. They asymptotically converge to the idealized analytic solutions in the limit of infinite discretization. We seek to compare how physical and numerical dissipative mechanisms change solutions to partial differential equations. These two different types of solutions are compared in the context of an ambient fluid flow problem and a wall problem. We observe the kinetic energy and specific entropy density in the ambient fluid problem and other thermodynamic state variables near the wall in the wall problem. In the ambient fluid and wall problems, we consider the Euler equations with the addition of viscosity and heat conduction. The vanilla Euler equations are conservation equations that govern fluid dynamics in the inviscid non-conducting limit and form a hyperbolic differential system. We add to these equations the dissipative, irreversible, and non-hyperbolic terms of viscosity and heat conduction to represent momentum and energy diffusion, respectively. These added terms are labeled with the yellow arrows in the conservation equations below. How to begin to analyze these equations? One thing often done in mathematical and numerical physics is the massaging or manipulation of a differential system to make it easier to solve. Here we non-dimensionalize the modified Euler equations with the definition of new and non-dimensional variables. The first variables introduced are space and time, which allow us to rewrite the derivatives. Then new flow and thermodynamic/state variables are defined and placed into the differential system. The selection of a suitable equation of state allows us to rewrite a third state variable. The manipulation of the added constants, rho naught, E naught, etc., allows us to define non-dimensional energy ratios Ke and Km. Ke is the ratio of energy in the translation degrees of freedom for a gas to the thermal energy of that gas. Km is the ratio of translation degrees of freedom to the energy contained in a sound wave. Further manipulation of the constants allows us to write both the Peclet and Reynolds number. These numbers tell us about the ratio of inertial effects to both heat conductive and viscous effects, respectively. The final differential system now discretized is boxed in the bottom right. The differential system just boxed was discretized via the method of lines. RK4 was used as the temporal integrator. A sense of this is shown to the right. In the bottom left, an error plot can be seen where a simulation of the semi-analytic solver at a 5,000 point resolution simulation was taken as the analytic solution. Fifth order convergence is observed in the L infinity metric. The semi-analytic solution was also compared to a well-verified and validated finite element code run with the same initial conditions for both the ambient fluid and the wall problems. This may be seen in the bottom middle and bottom right plots. Note the excellent agreement. Having shown the differential system we are solving and verifying the semi-analytic solution produced, We now begin our analysis of the locally negative entropy production, wall heating effect recovery, and viscous solution comparisons. Entropy production is a side effect of the inclusion of irreversible terms in a differential system. In the top left plot, we show how the kinetic energy of the simulation changes as a function of non-dimensional time when different irreversible terms are included. The energy differences are tabulated in the bottom left, where we can see that the energy that goes toward entropy production Q in the viscous conductive simulation is roughly equal to the kinetic energy difference between inviscid and viscous conductive simulations. These physical values for viscosity and heat conduction show an implication of what the inclusion of certain numerical operators with effective numerical dissipation would do. This mutation of the differential system contributes to negative local entropy production, see the plot on the right. It should be noted, though, that only the inclusion of heat conduction allows for negative local entropy contributions. Another side effect of the inclusion of physical dissipative mechanisms is the recovery of wall heating effects as observed by No. Physical effects reproduce the qualitative behavior associated with the inclusion of artificial viscosity in the No problem. The sole inclusion of physical heat conduction, however, in a semi-analytic solution produces the opposite effect. The combination of these two effects, Q and H in No's paper, in the viscous conductive solution non-linearly combines them to approximate the inviscid solution. This balancing of the two competing effects suggests that the inviscid solution may be recaptured by iteratively probing the parameter space associated with the Peclet and Reynolds numbers. The recapturing of qualitative effects by simply including in the differential system dissipative terms speaks as to the implication of numerical operator mutation of differential systems. We have shown that the inclusion of Q and H approximates not an inviscid solution, but instead a viscous conductive solution. The use of certain numerical schemes irrecoverably alters the differential system, and the resultant solution only converges asymptotically to the ideal analytic solution in the limit of zero mesh size and zero dissipative term influence. So what's a direct comparison of how numerical operators really mutate underlying physics? Well, we can show a comparison between our physical dissipative viscosity and two viscous effects in a finite element code: numerical viscosity implemented via Cauchy stress tensor and von Neumann artificial viscosity. Note the excellent agreement between the semi-analytic physical dissipative viscosity and numerical viscosity. Physics is recovered. However, when artificial viscosity is implemented, we note that a physical length scale associated with physical viscosity is recovered at one resolution. This changing length scale of the numerical operator mutates the fundamental underlying physics in an asymptotic manner. A truly viscous solution is approximated, not an inviscid solution. One might imagine how the inclusion of more than one numerical operator, especially if done in a black box, might negatively evolve the numerical solution away from the idealized physical solution. The inclusion of numerical operators, especially unexplored ones, may give rise to several undesired or misunderstood results. For example, the inclusion of an effective heat conductive term, a second derivative energy term, by some numerical operator like upwinding can lead to locally negative entropy production. In addition, we have shown that the qualitative effects of wall heating have been recovered by solely physical quantities with the viscous solution mimicking wall heating effects, the heat conductive solution opposing those effects, and their combination balancing them to approximate an inviscid solution, but never truly be inviscid. There is introduced a fundamental difference between the viscous conductive solution and inviscid solution to the differential system. In our viscosity comparison, we showed how a numerical operator mutates the fundamental underlying physics in an asymptotic manner. The solution was not an inviscid differential system solution. One might imagine how the inclusion of more than one numerical operator, especially if done in a black box, might negatively evolve the numerical solution away from the idealized physical solution. The verification of numerical algorithms depends on the fact that scientists and engineers are correctly approximating the discretized equations they are solving. However, if those equations are mutated by numerical operators, physics not present in the analytic solutions can appear in a numerical solution, leading to inaccurate/inappropriate verification and validation results. References used in this work. Acknowledgement of the individuals without whose work these results would not have been possible. Thank you for your time, and I hope you enjoyed this presentation.